Today I'm starting states of matter. Now, this is the topic of as chemistry, the states of matter. So, student, listen lecture clearly. I am giving you the guide according to the your past paper solution. Okay, I will guide you according to the your past paper solution. For example, there is a container, a cubical container. In this container, there are molecules present, gases molecule present, and these molecules are, we know the molecules of the gases are moving freely in every direction in a container. Molecules which are present in a container moving freely. Molecules in a container, these are the molecule of the gases. Molecule in a container moving freely uh, in every direction and colliding with the wall of the container. Okay, for example, these are the molecules present in the container, and these molecules moving and colliding with the wall of the container. When these are colliding with the wall, these are applying the force on the wall. Colliding and applying the force. Colliding and applying the force. Collision is basically applying the force. And when force per unit area apply, its mean pressure is formed. When force per unit area is applied, force of the collision or the molecule per unit area apply on the container, it is forming the pressure. When molecule are applying the pressure on the container, volume increases, okay? For example, container is joined with freely moving pistons and molecules present in the container colliding with the container, applying the pressure. When molecule applying the pressure, the volume increases. Pressure insidely when apply, volume increases. When we apply the pressure on the molecules, on the container, what happens? Volume decreases. When outsidely pressure apply, the volume of the container is decreasing. Insidely, when pressure apply, molecules applying the high pressure on the walls, the volume increasing. When outsidely pressure apply, volume decreasing. It's mean when we apply the pressure on the this molecule pressure increasing due to the temperature when we apply the temperature. When we apply the temperature, molecule pressure inside the container increasing and volume increasing. It's mean temperature directly proportion to volume. Mean temperature increases the volume. We can say volume and temperature both are directly proportional. When we apply the pressure outsidely on the container, now what's happened? Volume decreasing. Mean pressure inversely proportion to volume. When we apply the pressure, gas is present inside the container. When we apply the pressure, what's happened? Volume decreasing. When molecules applying pressure insidely due to increase in temperature, then volume increases. In this condition, we say volume directly proportional to temperature. And pressure, when we apply volume decreasing, it's mean pressure inversely proportional. When one quantity increases and other quantity is decreasing, it's mean there is a inverse proportion. Okay. Inverse proportion graph is basically like that. pressure and volume. Pressure decreasing, volume increasing. Pressure increasing, volume decreasing. There is a pressure increase and volume decrease. You check in graph, pressure increasing and volume decreasing in every increase. Volume decreasing going down, and pressure you check when you connect the graph, pressure increasing, both are directly proportional. When we make a graph between the pressure and 1 upon of the V, now this is the direct. When we graph make between P and 1 upon V, now this is the direct graph. 1 upon V whole quantity and the P, both are the directly proportion to the volume. Its mean total is that pressure applying and volume decreasing, pressure and volume both are uh, basically inversely proportional. Pressure increasing, volume decreasing. And what's happened when we apply the pressure or volume decreasing? What's happened? Volume is decreasing. Volume decreasing. Molecules are coming near to each other. When volume is greater, then molecules easily move. When pressure increases, volume coming nearest to molecules coming nearest to each other and colliding more frequently. Now the collision increases. When rate of collision increases, now it's also increase the pressure. When we decrease the volume, what happens? Pressure increases. Or when we increase the volume, decrease the volume, then pressure increases. When we increase the pressure, volume decreases. Both are react inversely. One increase, one decrease. Okay. When we directly made the graph between the volume and the pressure, now this is inversely proportional graph. When we make a graph between P and 1 upon V, inverse of the V, then this is the direct graph. Okay, must remember this graph and what's happened when the pressure increases. Now, similarly, when we increase the temperature of the container, volume increases. If, for example, molecules are present in a container in which the one side of the or the floor of the container moving easily, when we apply the temperature on the uh, uh, container, when we apply the temperature, increase the temperature, what happens? A molecule colliding more frequently. When molecule colliding more frequently, pressure increases and the volume increases because this piston can move easily. Now, when one floor or piston moving easily, we check here the volume directly proportion to temperature. Volume increase is also producing the high uh, temperature, also producing the high volume, and volume directly proportion to the temperature. We can say volume directly proportion to the temperature. Temperature increases, volume increases. Now, what's happened when we apply the pressure and what's happened with when we apply the temperature, what happened with the pressure? Now, when we increase the temperature, pressure of the molecule increasing, mean both are directly. Temperature and pressure both are directly proportional. When we increase the temperature of the molecule, molecule collision increases and more frequently colliding with the wall of the container. Now, what's happened? Temperature increases, pressure increases. When we increase the temperature, volume increases, both are directly proportion. Mean temperature, pressure directly proportion, volume, temperature directly proportion. But pressure and the volume both are inversely proportional. When we increase the pressure of a container, then volume decreasing. Now, these are the inversely proportion. And when we draw the graph between the volume and pressure, like volume is the inverse here, 1 upon V, then a direct graph form. Clear, student? What is the relation between volume, temperature, pressure? Now, these are the some gases law in which I told you about the relation between volume, pressure, temperature, volume, and uh, pressure and the temperature. Now I'm coming towards the kinetic molecular theory of the gases. Kinetic molecular theory of the gases. What is the kinetic molecular theory of the gases? Now there are some postulates, some points of this theory. With the help of these points, I can explain. I will tell you about the kinetic molecular theory. According to this theory, first, molecules are moving with constant random motions. Molecules are moving. First point of this theory is that molecules are moving uh, basically constantly. When molecules are moving, it's mean the kinetic energy present in the molecules. Molecules moving constantly. This is the first point because there is kinetic energy present in the molecule by which molecules moving. Kinetic energy present in the molecules. Molecules moving according to theory of the kinetic theory of gases. Molecules moving constantly in a gas. And the gaseous molecules are uh, moving very fastly. The movement of the molecule is very fastly. In the gases, okay? Very fastly. And randomly, mean all direction. Randomly. There is no particularity in the direction. Molecules moving fastly and randomly. Because these are the molecule. Kinetic energy of the molecule of the gas is higher than the others, like liquid or like solid. The energy of the molecule is higher in the gases molecule kinetic energy. Due to kinetic energy increase, molecules moving very fastly or randomly. Secondly, the molecules uh, having no fixed volume. The molecules hardly having a volume because the volume of the particles is negligible. Molecule of particle is negligible, mean very small volume. We neglected it. Volume of the particles negligible, very less volume, negligible volume as we compare to the volume of the container. This is very less volume and hardly we consider the volume. Volume is very less in the gaseous particles. Every particle having less volume in gases also. Uh, we consider no volume. The gaseous molecule do not attract to each other. Their uh, internal attraction is very low. It means no intermolecular forces. Intermolecular forces is very low. Kinetic energy is higher, its mean potential energy is lower. Intermolecular forces very low. Particles moving fastly in every direction randomly. We consider the volume, neglected the volume. Volume is no volume of the particles. or the particles intermolecular forces are very low in the gases. That's why molecule freely moving in the gases. When these particles are colliding, no loss of energy form. It's mean the motion is the elastic motion. When uh, molecule of the gases colliding with each other, there is no loss of energy. These are colliding with same energy. After collision, before the collision, collision with wall, collision with molecules, in every collision, there is no loss of energy. Molecules colliding and their collision elastic. Elastic means there is no loss of energy formed between the molecule. And temperature is directly proportional to the kinetic energy of the molecule. Temperature directly proportional to kinetic energy. When we increase the temperature, kinetic energy of the molecule increases. Temperature directly proportional to the kinetic energy of the molecule. Now, these are the some concept relating to the kinetic molecular theory of gases. Molecules are moving randomly in all directions. Molecules moving fastly. No intermolecular forces. Potential energy is lower. Kinetic energy is higher. We neglect the volume of the particles. Particle is colliding. Their elastic collision is formed. Mean there is no loss of energy formed when particles are colliding. Now I'm coming towards the ideal gases. What are the volume of that an ideal gas occupies depend on the its pressure, its temperature. Changing gas volume mean uh, we say the volume of the ideal gases depend on the pressure and temperature. Now we have studied it. If temperature increases, volume increases. If pressure increases, volume decreases. It's mean volume depend on the pressure and the temperature. And when we heat the gases, what happens? The molecule collision increasing, their kinetic energy increases. When we heat up the gases, what happens? Due to heat or increase in temperature, collision of the molecule increases. When collision increases, pressure increases, and collision increase also increase due to the kinetic energy of molecule, because molecule moving with now higher energy and more colliding. When colliding, then pressure increases. It's mean temperature and pressure both are directly proportional. Pressure increase also apply the force on the wall of the container if this may result the volume increase. Volume directly proportional to the temperature. These all are connecting with each other. Temperature with collision, temperature increase forming the more collision, kinetic energy increases, then pressure increases. When we increase the pressure, volume decreases. These are connecting to with each other. Now, increase in temperature, we know that increase the kinetic energy of the molecule. When kinetic energy molecule increases, it's mean volume and temperature. If container can move easily or can expand easily, then the temperature increase also increase the volume. It's mean ideal gases are that those type of gases which obey all the gases law. Ideal gases are that type of gases obeys all gases. Volume, pressure, boils, stalls, or all type of law may be applied in the situation of the ideal gases. And what are the limitation of the ideal gases where there is a lag? Uh, at very high pressure and low temperature, real gases do not obey the kinetic theory of the gases. When the high pressure form and high temperature form and low pressure form. When high temperature and low pressure, in this condition, they are not obeying the gases law. When we talk about the ideal gases, these are not obeying the gases law. When the pressure is higher, and when the pressure is higher and temperature is low and the pressure is higher. When the pressure is higher and the temperature is low. When the pressure is high and temperature is low in this condition, ideal gas is not obeying. The gases or molecules are close to each other and very near to each other. They are instant induced dipole, uh, permanent dipole, permanent dipole forces between the molecule. Due to these two property, no ideal gases are not obeying the law. What happens when the due to high pressure molecules come to near each other and their dipole interaction increases, and by due to which molecule cannot obeying easily the all law. When there is a no force, molecules can obey the law, but when the high pressure molecules come from air, now force increases, attractive forces increases. Now the gases molecules cannot obey in this condition. When the dipole forces and induced forces increases, gases molecule cannot obey the laws due to this condition. When the pressure is low, molecules are near to each other and dipole attraction increases. And what happens? No molecules pull away from the container walls. When molecules comes near to each other, now pull away the container wall. Basically, when molecules are moving freely, striking with the wall easily and applying the pressure on the wall. And that's for pressure, no, the lower on the wall of the container. Now there is the ideal gas equation. We apply the general gas equation for the ideal gases, PV equal to nRT, in which P is pressure, V is the volume, N is the number of mole, R is the general gas constant, and T is the temperature. And numerical is also coming related to this topic in the ideal gases. Now I'm coming towards the lattice structures. In a state of matter, we also consider the lattice structure. Most ionic, metallic, and covalent compounds are crystalline lattice, having crystalline lattice. I mean, their shape is present in the. Now, this is the lattice structure. Most of the ionic and covalent compounds are having the crystalline lattice, means shape present in their molecules. Molecules are arranged in a regular and a repeating arrangement. Now, there is a repeating arrangement present in the molecule. Now, this is showing that a crystal lattice. Now, when the ionic, metallic, and giant covalent structure. metallic, ionic, and giant covalent structure. These are having a regular shape pattern. No, these are having crystal lattice pattern. Now, what are the giant ionic lattice? An ionic compound is an electrostatic force between the compound positively and negatively cation present in the ionic compound. Now, these forces make a fixed arrangement of the particle. Now, this fixed arrangement of particle forming a crystal lattice in the ionic compound. And these are the ionic lattice. Also, covalent compounds having giant covalent compound having a lattice structure. Now, in ionic compound, positive and negative ion arrange in a regular pattern. Positive and negative ion arrange in a regular pattern. Now, this is the crystal lattice, and in also giant covalent structure, this crystal lattice are present. And carbon also having a their crystal lattice forms structure in graphite also. And silicon atom also having a crystal lattice structure. These are the giant structure. Carbon having in the form of diamond and graphite also lattice structure. And when sodium and iodine or sodium or chlorine both are combining, these are also forming in the ionic structure crystal lattice. Crystal lattice present in the ionic structure. Giant covalent structure, carbon atoms like graphite and graphite or diamond or in the silicon atom, these lattice structure are present. In metal also there is a lattice structure present. Metal also having a regular arrangement of the atoms present in it. Now, what is the effect of the bonding and structure on the physical properties? Bonding mean ionic bonding, covalent bonding, or metallic bonding. What are the effect of these? Now, I will tell you all these properties in the next lecture. Okay, student? Allah Hafiz.